Good morning, everybody. Good morning, everybody. We will get started here in just a second. Does that show pretty much everybody so far has joined, Becky?
Yes.
Okay. Welcome to the Ohio Federal Research Network's Opportunity Days for this quarter. So this one is focused on hypersonics, which is one of the teams that we have working for round 6 for OFRN. Next slide, please. Just a quick agenda. So I'll just provide a short overview here, and then we'll get into the important part of the hypersonics opportunity day, which is the presentations by two of our esteemed researchers and presenters for today. And then, as always, we will finish up with a short opportunity review by Morgan, and then wrap it up. For Q&A purposes for this, you can raise your hand, you can put something in the chat at the end of each of our presenters talks, and we're always looking forward to interaction with our audience on these. Next slide, please. Again, just the introduction. So I'm Mark Bartman, the VP for Advanced Development, Parallax Advanced Research, and our Parallax team, Becky Mesher, Lauren Jones, Jess Pacheco, and John Jackson, our work on putting these together, our event speakers today, and I'll do their introductions here shortly. And our opportunity review, as I mentioned, Morgan Buck, who is an intern at Ohio State University for Parallax Advanced Research. And of course, thanks again to our government partners, the Air Force Research Lab, Navy Medical Research Unit in Dayton, and NASA, the Glenn Research Center, and the National Air and Space Intelligence Center, and of course, the Ohio National Guard. Next slide, please. So just a real quick, for those that maybe aren't super familiar with how OFRN is put together, we have, as I mentioned, those 5 federal partners that we just talked about. The funding for Ohio Federal Research Network is 100% from the state of Ohio through the Ohio Department of Higher Education. So we appreciate the partnership and the support that ODHE provides to this program. It's based on meeting those industry and federal partner needs for that. Parallax and Ohio State University are the administrative arm of the program. And that's really all we do, is administer the program. So all the decisions are made by either the federal partners or our technical review council or the executive review board when it comes to funding. Next slide, please. I call this our bubble slide, but it's just kind of a roll up of sort of our impact to date on the things that we've done and the people and places that we have collaborated with around the state of Ohio. You can see so far we're up to 23 universities and colleges have engaged in the 41 projects that have been funded so far over the 8 years that we have here. And sorry, I'm having an issue with my computer. The number of direct jobs that you can see there, I think, is pretty significant over that 8-year period for that, and also as well as the number of startups that have come out of this particular program. But really, the big numbers are the bottom line down there. Is so far the state of Ohio has put in almost $62 million, and out of that, we've had follow-on funding. The vast majority of that is from the federal government. That have been awarded to the teams that have participated in OFRN. And then, as I think is important to show that both our industry partners and our university partners feel that this is an important enough program that they've contributed a significant amount of cost share as well to make this work and be successful. Next slide, please. Just a very quick update. The relatively new program, about a year old, that I manage along with my program manager, John Owen, is the Defense Innovation Unit OnRamp Hub Ohio program. And our partners with that are Dayton Development Coalition, Jobs Ohio, and One Defense. Next slide. Just real quickly, so the OnRamp Hub is just, as it says, it's kind of a front door to innovation. It's a way to hopefully more quickly connect companies that have solutions that are already higher TRL level, that maybe are non-traditional partners with the Department of Defense, that are looking to be able to bring the technology solution that they have to bear to support our men and women in uniform and around the globe. We also offer some classified workspace as well. So if you're a small business looking to get into opportunities in classified work and has a government sponsor that's willing to help you, then we can support you in that need. Next slide, please. There are 4 other states that right now anyways that are part of this program, Arizona, Hawaii, Kansas, and Washington. And we all work very closely together. We collaborate. We're in meetings every week to talk about opportunities around the country and ways that we can connect industry to the Department of Defense for that. Defense innovation will probably add 4 or 5 more states here over this next year to this program, which will further deepen the connection that we have to regions here throughout the country. Next slide, please. And then this is just real quickly. And by the way, everybody, you'll be able to access these slides on the OFRN website here after we're done today for that. So if you're trying to quickly take screenshots or something, you don't need to do that. These will all be available to you for it. But this sort of inverted pyramid is just a very quick way to illustrate the method that we use when it comes to how we connect companies to the department to solve technology issues. Next slide. Program that I wanted to mention really for today, not new, but right now for those of you that track SBIR and STTR opportunities, the Air Force just opened up their most recent open call for technologies out there. So Parallax also manages a partnership intermediary agreement for the Air Force Research Lab called the Academic Partnership Engagement Experiment, or APEX, not to be confused with the APEX Innovation or Innovators that are those smaller organizations around the country. I know Ohio, I think, has 4 or 5 locations for that. So this is specifically a partnership intermediary agreement. They did recently this year, they expanded the opportunity to work with all of the services within the Department of Defense, not just the Air Force. That was a recent change to some of the language that governs the way that they operate for that. And you can see what their nationwide impact so far has been over the last couple of years. This was stood up around 2019, if I remember. So it's been around about 4 or 5 years. Next slide. And this really is kind of the one that I really wanted to highlight, just to show the success that they have had in doing this. And you can access the folks that work with Apex either through Becky or myself, or you can go on Parallax's website and also the Apex website to make connections with the team that does this on it. The one thing that I do want to highlight is which is highlighted in yellow on the right-hand side of your slide, is the fact that to date they have helped companies make that transition across the valley of death to phase 3s or program of record type funding for 11 companies that have done that. Next slide, please. Alrighty, so that's it for us. And as you can see, there's the emails on here, and as well as the OFRN website, which actually I guess we don't have on there. Should probably have on that, Becky. Next slide. and we'll get into the important part of today. Let me do some quick introductions here, and then I'll turn it over to Dr. Camberos. Dr. Camberos is recognized for exceptional and sustained contributions to development and dissemination of multidisciplinary methods for aerospace vehicle systems integration, analysis, and design. At the Air Force Research Lab High-Speed Systems Division, he led a team of engineers in developing multidisciplinary analysis and design capability for high-speed systems. Currently, he serves as the director for the Applied Research Center for Hypersonics and associate professor in the Department of Aeronautics and Astronautics for the Air Force Institute of Technology at Wright-Patterson Air Force Base. So, sir, I will turn it over to you to start your presentation.
Thank you, Mark. And I do want to say I appreciate the opportunity. Anytime I get a chance to talk about hypersonics, I just can't turn it down. So thank you for that. Thanks to Parallax and the great partnerships you guys have established there. I'm a big fan, and I'm glad to see that the Ohio Federal Research Network is benefiting the state of Ohio in such a great way. Let's go ahead to the next slide. As Mark mentioned, my name is Jose Camberos. I'm the director for the newly established Applied Research Center for Hypersonics here at the Air Force Institute of Technology, AFIT, if you will. And you can read there our mission. It's really, I'll highlight, it's defense-focused challenges in hypersonics. We deliver education and workforce development opportunities through, of course, teaching, which is our mission, of military and civilian folks here at Wright-Patterson Air Force Base. We conduct basic and applied research, and we also provide subject matter expertise through the various researchers, both professors and other researchers, research fellows that we have here at AFIT. Next slide, please. A little bit about me, my background. I like airplanes. I'm a big fan of airplanes ever since I was a little kid. These are some of my favorite from World War II. You might recognize some of this. And for those of you that are going to stay here till the end, there will be a quiz at the end to see how many of these you can identify. No. Next slide, please. With advances, primarily military advances, of course, through the Cold War, we saw the shapes of airplanes changing and evolving as we advanced and developed the technology that gave us the capabilities that allowed us to become the world's most powerful air force in history. Next slide, please. And of course, what we're here to talk about today is really the high-speed kinds of systems that we are currently pursuing and developing. There's a worldwide interest, as you well know, in hypersonics, and the Air Force is definitely investing, our Department of Defense is investing significantly in developing, evolving, and maturing, transitioning the technology to make systems, legacy systems like this, continue to evolve and improve and field a capability for our defense. Next slide, please. First, I'm going to talk a little bit about AFRL. I structured this presentation to include, if you saw the disclaimer on the first slide, this is distro A material. And the second portion of this, I'm going to touch very generally on what is hypersonics, as well as how do we approach the development of hypersonic technology from the perspective of systems development, systems engineering, and systems integration. AFRL has a mission to support both the Air Force and the Space Force through leading technology development, including the basic research through applied, through discovery, through development, and then ultimately through transition of that technology for our air and space defense. Next slide, please. The way that this AFRL, the Air Force Research Lab, operates is they have this 9 technology directorates plus one that specifically supports academia. That's basic research. That's our Air Force Office of Scientific Research. The color coding here on these little note cards on the left, you see the 4 blue ones. These are headquartered here at Wright-Patterson Air Force Base. They include the Materials and Manufacturing Directorate, Human Performance, Sensors and Aerospace Systems Directorate, where I spent the bulk of my career working at FRL. In the middle there, the Space Vehicles and Directed Energy Directorates are headquartered in New Mexico, Albuquerque, New Mexico. And then next to that, the gray boxes towards the right, the Information Directorate is in Rome, New York, and the Munitions Directorate is in Eglin, Florida. The Air Force Office of Scientific Research, where anybody working in academia should be partnering with in terms of basic research, they're headquartered in Arlington, Virginia. The experimentation is spread throughout the various locations where the Air Force Research Lab has a presence. You can read the details of this. As Mark mentioned, these slides will be made available. And I'll give you also a website where you can check out and find some more. Next slide, please. The way that the Air Force Research Lab invests their funding, which comes from congressional and presidential action, is through basic research, where a good chunk of money is invested primarily through the Air Force Office of Scientific Research and other ways that we utilize that to basically discover new things, test new ideas, ask what-if questions. The bulk of our funding goes to applied research. The numbers here are just the way that our congressional budget allocates the funding and tracks it. This is intended to develop the science to application. Primarily, we've done some discovery. We figured out the physical phenomena, and now we're ready to do some benchtop or smaller scale experiments. Next to that is the advanced technology development, where we also have significant investments into actually getting out there, develop the hardware, fly things and develop things and implement them in field experiments and tests. Other Air Force funds that are executed support small business innovation, SBIR program through the AFWorks program, experimentation, and among other investments that are made to small businesses and also the academic community for supporting the non-research and technology development. And these numbers, by the way, this is FY18 data, so we're a little bit behind here. The most up-to-date slides here, those numbers would reflect the current investment. And they have jumped up primarily because of the investment that the Air Force is making in hypersonics and other fields. Next slide, please. Here's the locations by state. So those of you that may be participating with Ohio entities, but located elsewhere, there are ways to partner and ways to contact and work with Air Force Research Lab across the country. There's also, we have sites in Hawaii at the Maui Research Site where we have some observatories. We also have an international presence in London, Tokyo, and Santiago, Chile, where we fund small-scale proposals, projects to keep tabs in the international research capabilities so we can harness the power of other ideas by making these investments and then hopefully bringing them into the fold for supporting our defense worldwide. Next slide, please. Here's a small list. It's not exhaustive by any means, but it shows the world-class facilities and state-of-the-art capabilities here. Each of these, some of these are world unique, and some of these are located in the various locations that you saw in the previous slide. I'm most familiar with the middle one there, the hypersonic wind tunnel that's here at Wright-Patterson Air Force Base that has Mach 6 capability. It's a blow-down tunnel, so you can see the big sphere there where the air is pressurized, released, and then we funnel that through the test section. Also, the radar towers are located here at Wright-Pat. Those are these giant towers that are supporting our sensors directorate. And of course, to support the computational needs, we have access to supercomputing resource centers, not just here at Wright-Patterson Air Force Base, but also in other facilities across the country. The things that we share also with the Navy and the Army and others, NASA, of course. Florida, we have some of in our munitions directorate, we have facilities where we can detonate things, blow things up, and test things that go boom in various areas at Eglin Air Force Base. Of course, we also do some of that at Edwards Air Force Base, where we can test some of our rocket facilities, which are not shown. Well, the one shown here on the upper left-hand corner is there at Edwards Air Force Base. All right, so next slide, please. Again, just a sampling of the facilities available. If you're interested in where the Air Force is investing money, of course, quantum computing is a big thing these days. We are at the cusp of making significant breakthroughs. As you well know, it's public knowledge that quantum computing is here to stay, and definitely it's something that we will be continue to invest in. Artificial intelligence and autonomy, this has been ongoing for years before it became a thing these days with ChatGPT and other more publicly accessible AI and machine learning type tools. Directed energy weapons are also one where the Air Force and the DoD is significantly investing. We're not quite at Star Wars level yet, but you can imagine where we might be going with that. And then last but not least, hypersonics, my area of interest. We are investing in the capabilities that will support our ability to field hypersonic systems now and into the near future. Next slide, please. So how do you partner with AFRL? There are a variety of ways that you can do that. So, we should count OFRN, the Ohio Federal Research Network, as a part of this ecosystem, if you will, of ways to collaborate that. You can get a lot more information at the afresearchlab.com webpage, where you can find out more about each of the directorates, points of contact, how to apply for everything that you might want to need for small businesses, for scholarships, fellowships, internships for students that may be interested in working in these areas. And of course, you can always check fedbizops.gov for solicitations for proposals. We have various centers also to support that. And one last thing on this, check out YouTube. We all like to watch YouTube, right? We probably don't want to admit how many Saturday mornings we probably wasted in doing that. But check it out. It is look for AFRL Inspire for a sampling of videos that AFRL has put out there on its innovative work that's being done. Next slide, please. Okay, on to hypersonic vehicle technology and some major developments. From here on, the slides are stuff that I used when I've taught classes in hypersonics at the University of Dayton and at Wright State University on this. Next slide. It begins actually, believe it or not, soon after the Wright brothers flew. Well, for this seminar, I'm going to talk about hypersonic flow, how we need to understand the relevant physical phenomena that drives our approach to how we do hypersonic vehicle analysis and design. Next slide. It's all about the heat, as I like to say. AFRL has identified hypersonics as a game changer, so to speak. If you're interested in some of the history behind hypersonics, there's a great book by T.A. Heppenheimer. It's publicly available. It is a NASA PDF publication. You can search for it on the web and obtain it. It's a great historical read all the way from essentially the Bell X-1 onto the NASA program from the 1990s. Next slide, please. All right, some of my favorite books on hypersonics. If you'd like to learn more, we do use John Anderson's book to teach hypersonics. There's also another one from an engineering perspective by Professor Bertin, who unfortunately passed away, but he was at the Air Force Academy for many years. And another book on hypersonic flow by Professor Rasmussen from, I think it's either University of Oklahoma or Oklahoma State, one of the schools in Oklahoma. Next slide, please. And through the, if you have access to the Ohio libraries, ohiolink.edu, if you belong to a university, you have access to some great resources too. Some of my favorites are by Herschel on aerothermodynamics and design problems associated with hypersonic vehicles. And of course, I already mentioned Heppenheimer's, and a whole slew of magazine articles, technical papers, etc. in the popular literature. Next slide, please. So back to the technology. Believe it or not, soon after the Wright brothers flew, there was already wanting to go faster and better, and the technology was starting to catch up. Germany had a plan to develop essentially a hypersonic system that looked like this, proposed by Eugene Songer and Arne Brett. Fortunately for us, this would not have been, if they had tried this, it would not have been successful, just because of the understanding of the phenomena at that time had not been sufficient to drive the design. Might make a good supersonic vehicle, but probably not the best for hypersonics, as we'll see later. Remember that it's all about the heat. Next slide, please. The Air Force was investing heavily in this area after the Bell X-1 and other successful testing. They had an idea to have a reusable hypersonic reentry vehicle that they called the X-20 Dinosaur. And there was some plan to develop this. You can see the different configurations there that would allow us a space access at different orbits. And unfortunately, the program was canceled in '63. The problem was that it had no viable military mission. It was too expensive for a research vehicle, and the funding went elsewhere. The other lesson learned here, of course, is do not name your program after an extinct species. It just gives it bad optics. So next slide, please. The X-15, one of the most successful hypersonic programs that we've conducted from the 1950s to the 1960s. 199 flights out of a planned 200, and the only reason the last one didn't take place is that, of all places, in Southern California at Edwards Air Force Base, it snowed on the day that they were planning that last flight. 3 vehicles were produced. We lost one. One is hanging at the Air and Space Museum in Washington, D.C. The other one is right here at Wright-Patterson Air Force Base. Come and enjoy it. Those of you that are in Ohio, come visit the Air Force Museum. I'm happy to go there, meet you there anytime. I need no excuse to go to the museum anytime for anyone that would like to enjoy the airplanes there. Next slide, please. More recently, we tried to advance the technology in the 1980s and 1990s with the National Aerospace Plane concept. And unfortunately, we tried to rely too much on computational capabilities that weren't quite there yet, and reduce wind tunnel testing. We asked for too many miracles, and this technology remained a paper study. We did expend a lot of money in the research, but the design just could not be achieved. Next slide, please. More recently, we have the X-43, the HyperX program. It's a demonstrator program where it had the flight objectives were really a test of the scramjet technology. This utilized hydrogen as the fuel, and it worked. As far as a test program was concerned, this was a highly successful program that NASA led for our country. Lots of good wind tunnel testing was performed, and it really pushed the advancement of hypersonic technology significantly. Next slide, please. Soon after that, the Air Force also took the challenge to get partnering with Boeing and others to develop the X-51. Believe it or not, this is considered a successful program, even though if you look at the details of each of the attempted flights, 4 flights total, some of them worked and some of them didn't. And when you do testing experimentation, the percentage I've been told is considered successful is 50%. So if half of your things work, you're doing really good as far as testing, because we're testing new technology. This was a hydrocarbon-powered scramjet engine. You can check out the video on YouTube. Just look for X-51 Wave Rider. Next slide, please. So hypersonic flow, as most of you may know, this is what we teach. Most experts agree that it is around Mach 5 is when we do it. There is no any magic number where that changes. It's just that certain things begin to happen when you get close to that Mach number. The air behaves differently than our mathematical models, thermodynamic models tells us, as it does in subsonic flow and transonic flow. Next slide, please. So Mach 5 is around, what we really look for is the physical phenomena. And the features that we look for, of course, it's high Mach number, thin shock layer, viscous interaction, high temperature effects. Remember, it's all about the heat, possibly low density flows. You can read more about this in John Anderson's book. Next slide, please. Of course, you want to be mindful of these viscous interaction. One surprise that happened with the X-15 program is we had the bright idea of attaching a dummy ramjet engine to test out that technology. And unfortunately, someone missed doing their homework here, because the shock interactions with the pylon there we almost lost the vehicle in this case. I think I can't recall if the ramjet engine was still attached when they landed or not. But as you can see, the shock interactions burned a hole. That is a very strong material, nickel chromium alloy, and the shocks impinging on there were burning through it like the proverbial hot knife through butter. Next slide, please. So you want to be mindful of the physics that occurs. You also want to be mindful of your models for predicting the things that are going to affect your design. In this case, a breakthrough occurred in ballistic atmospheric entry by Julian Allen and A.J. Eggers, who determined that the heating is inversely proportional to the radius of your leading edge. That means that the sharply pointed vehicles are going to suffer extreme heat. So you really want to design reentry vehicles and be mindful of, even with high-speed vehicles, that the sharper you make your edges, the stronger the heating. That's one thing that I mentioned, alluded to earlier, when the German concept Silbervogel was very sharply designed. It would not have worked according to what we knew later on in the technology. Next slide, please. Okay, so the other thing that we learned with hypersonics is that it turns out it's very easy to compute pressure coefficients. The higher the Mach number, the better this formula becomes. It allows us to bypass the high fidelity CFD computations that we normally do and rely upon a very simple model. So that C sub P is the pressure coefficient, and it shows that according to the theory, it becomes Mach number independent. So once you reach the high Mach number to compute the pressure distribution over your vehicle, becomes a very simple calculation. Next slide, please. In fact, there are software programs available. CB Aero is one that's described in that paper by David Kinney. SHABP was the original name for it. That was developed here at Wright-Patterson Air Force Base in the formerly called Flight Dynamics Laboratory. For a long time, that was the standard bearer. And then in the 2000s, NASA invested in updating the techniques that are utilized to compute there. And now, of course, with computing power, we can decompose a vehicle shaped like this into small panels upon which we can get the pressure coefficient from the formula you just saw in the slide before. Next slide, please. The other thing you need to be mindful of is, of course, the high temperature effects. This is a control issue that was encountered in the early development of the space shuttle, where the perfect gas predictions and perfect gas tests told us that the shuttle would be stable. This is the pitching moment coefficient versus angle of attack. And if you are negative, you're good. If you're positive, you're not so good. And so what happened is that Mach 23, when the space shuttle was reentering, you are really dealing with equilibrium air, with air that it does not work like a perfect gas. We cannot model it as a perfect gas. And what that shows is that you needed a significant angle of attack in order to maintain stability of your vehicle. And that could only be done by actuating the flaps on the wing there. When they were coming in, it was just barely able to stay stable with the amount of deflection that was required. So this leads to us then to be mindful of the physics that are occurring so that you can maintain stability, be mindful of the shock effects that occur so that you can design and operate your vehicle according to what the physics will drive you towards. Next slide, please. Should probably speed it up here. I think I'm running. So things to note, you need to understand the physics. It's key to technology development. The relevant physics will strongly influence system design and performance, not to mention your cost. And then, of course, you need to, how do you get the physics? Well, it's going to be your mission. Your mission will determines the relevant physics. Next slide, please. So in order to do this, let's talk briefly about hypersonic vehicle design. How would you approach it? Next slide. It's really a systems engineering process. You need to integrate a lot of different components. It's not just, this becomes really complex with a hypersonic vehicle. This shows a notional tailless supersonic fighter where the idea here is that we want to couple all the disciplines, all the couplings. at the right level of fidelity early on in the design process. Next slide, please. So speaking of design, I'm not going to read the whole paragraph here. I just want to highlight the blue text in there. The secret to good conceptual modeling is to get the level of simplification correct. If you're going to be designing vehicles, you need to understand that you can't just take willy-nilly each different discipline required and plug and play. You need to be mindful of the level of abstraction that is being represented by each of those tools, each of those computational tools. If you try to do it too high fidelity, you end up waiting forever to get any results. And if you do it too low a level, you may miss some of the physics that are going to drive your design. Next slide, please. Conceptual design in our world is really about system to subsystem, maybe to component level. We call that level 0, 1, and 2 type fidelity. You can see the time frame required to do conceptual design can vary from weeks to months or years. We definitely, for our research that we do, Boeing, and Northrop Grumman, Lockheed Martin, they get into the detailed design where it takes years and sometimes even a decade or so to develop technology. Next slide, please. This is a cartoon version of what one needs to do given the mission requirements, which determines the physics. You put together your aero, your propulsion, your structures, and other models. You need to figure out what's the input and output of each of these. How do these interact? Couple them together, run the program, run the design, test to see if the mission requirements are met. If it's not, then you go back and do the loop. Once your mission requirements are met, then you can say, yes, we have a closed and feasible design. Next slide, please. This process can be expanded from initial design through conceptual design, through preliminary design to detailed design. It just it depends on what level of detail do you need for that, what tools you have available, what their level of fidelity is. It all begins with geometry. That's why we put that in the middle of the spiral. But once we have a geometry, a shape to work with, and then we can drive it with each of the different tools that we have to analyze its aerodynamic response, its propulsion needs, its flight dynamics, its structural, thermal, and other subsystems that may be needed. And you can decompose this to whatever level of detail is needed for your design. Next slide, please. So for dealing with hypersonic air breathing concepts, it's all about the heat, and you need to definitely be mindful of both how much heat your vehicle is being subjected to from the outside and the inside. This was the most challenging thing that we encountered with NASP. And in fact, it led to an unclosable design. The requirements that were driving that were just, we just did not have the material capability at that time to be able to sustain the extreme environment to which it would have been subjected to. Next slide. More recent, so recognize the strengths and weaknesses of each tool. Here you have a variety of different tools available to do hypersonic vehicle development. Next slide, please. We have some recent successes. This is my last slide here, so I apologize if I went over too much over the time. We, as I mentioned, the X-43, the X-51 wave right. Yes, we have had some more successes if you've been watching the news more recently as well. However, we need to continue to press the technology if we are to harness the power of hypersonic flight for our defense needs. Over, and I will take any questions, Mark, if there's still time.
Yeah, absolutely. No, we have a little bit of time here. So if anybody has any questions, you can, like, as I said, you can either post them in the chat, you can raise your hand, come off mute, and feel free to ask a question while you're all thinking about your questions. Maybe I will start off by asking one, which is how are the multiple disciplines connected or integrated across all of this?
That's a great question, Mark. And the way that these disciplines can be integrated for modeling purposes is through special techniques, either frameworks. There are some commercially available that allow you to take a software program that calculates, for example, the aerodynamic response of your vehicle, a different software program that does the propulsion calculations, And you need to be able, since a hypersonic vehicle is such a tightly integrated system, you need to be able to connect those two programs in a way that allows information to pass seamlessly back and forth. We have ways to do that through systems modeling language, for example. There are tools available that do that from an input-output approach. To name a few, and I'm not endorsing these by any means. There's Model Center, which used to be owned by Phoenix Integration, which I think has been absorbed by a different company. There's Mode Frontier available also, that basically provides a framework in which you can take your software, and it allows you a visual representation to input and output the data. That's one way. You can also do it on your own. We have Python code that we used in our Dash team to integrate the different software. What you want to do is automate. You don't want to be doing design by simply taking output files and then having to run a different program. Too much hands-on becomes time-consuming. And so you want to automate that process as best as possible. And we do that through frameworks. Over.
Excellent. Let's see. Any questions? I know everybody is shy early in the morning about asking questions here. So, looks like one popped up. Leon says, how can we present to this group via, I see, asking about, if you want to, you can send Becky a short summary as to what your expertise is and what areas you think that you would be able to present at. We're always looking for industry presenters, as well as from our federal partners on different topics. The key is, if you take a look at the OFRN website that Becky put there under round 6, you'll see our 6 areas of interest that we currently have. And so during the period of performance, which is about 18 months, so it'll run through next spring, what we try to do is have experts that are part of the teams or are working with the teams that will present on one of those areas of interest topics. So for instance, today happens to be hypersonics. So we do have, I think, a couple of questions here. So well, this deals with CyberSitter, so I'm not sure if this is kind of up your lane or not. He's asking about what makes a successful CyberSitter application. I think that might better fit with our Apex folks, which we're happy to connect you with them. Todd, if you can send Becky your email address, we will be happy to connect you with our Apex folks for that one. So
from the government perspective, Mark, I can also add to that, for SBIS CTR application, find a partner. Go to the AFRL Research or .com website that I posted, and find somebody in the technology that you're interested in. You need to find that because they can help you develop your proposal in a way that's going to really fit the needs that they're looking for. Over.
Excellent. I would like to second that as well. In my previous career, before I came back to government, I wrote several successful SBIR proposals for both AFRL and NASA, and I would absolutely agree with what Jose said. It's really helpful to talk to the people that are already working the area. You can get a really good understanding of what the technologies that are needed, what they're interested in, and it kind of helps focus your proposal more closely on what the government really is interested in at the moment. Mm-hmm. So second
Excellent. I do have one here for you, Jose. It says, would there be any interest in using quantum computing and simulation to accelerate the heat simulation, or CFD?
Absolutely. And Shenhua Jiang definitely caught on and was paying attention that in hypersonics, it's all about the heat. We need predictive tools that we can attach basically some confidence level to. If right now, it's I would say our predictive tools for computing the heat, you're talking 20% or more uncertainty. If we're going to drive the materials technology and inform our materials and structures engineers better, we need to bring that uncertainty to level down. In other words, our computational tools need to be better at computing the heat accurately and precisely.
Excellent. We did have somebody, Becky said that we had someone had their hand raised, but I don't see it
Yeah, that
now.
was Professor Carre from University of Cincinnati.
Yep. You can go ahead and come off mute. If you'd like to ask your question, if you still have it. Maybe while he's working on that, we'll do one more here. Let's see, from Kevin Busto about, he says, has there been work in the spectral range above 1700 nanometers, specifically chemical analysis of components before and after tests?
Who is that?
Kevin Busto
Okay. He
had a
typed
question.
something.
Yeah, he had a question that says, has there been work in the spectral range above 1700 nanometers, I believe, specifically chemical analysis of components before and after the tests?
Does he mean in terms of signatures or wakes or something like that?
Kevin, do you want to come off of mute and ask your question specifically?
Yes, hi. The reason I ask is that I've been researching chemical analysis above 1700 nanometers of the light spectra, and it looks like there's certain things that you can see in that range between 1700 and 2500 nanometers.
Mhm.
And I was wondering if you were doing some research in that area as well, looking at what happens to the components that are very highly susceptible to any type of change from being run at hypersonic speeds, and what change is there in that material, and how do we track that material?
Sure. So two things. I'm going to break that down into two parts. One, if you're interested in the sensors aspect, I'd recommend you visit the FRL research website and check out the sensors directorate. Anything related to either sensors or effects like that with hypersonics, unfortunately, I'd have to pull out my flashy thingy and erase all your memories if we talk about that openly. Over.
Awesome. Thanks, Kevin. Appreciate it.
Yeah.
We'll go ahead and
Okay. All right. Thank you.
you bet. We'll go ahead and if you have additional questions, you can go ahead and continue to post them for Jose, and we'll make sure we capture those.
I'll
and
try
get
to answer them on the chat. There is someone logged in with my name on there, but that's not me asking myself that question. I don't know who that is.
I don't know who that is either, but we did notice that you were logged in twice, so I'm not sure if you have a colleague there at AFIT that's decided to use your name.
What I think might happen is whoever logged in just typed in that name as the name of one of the speakers, I suppose.
Could be.
So sorry about that. When I downloaded the app and logged in, it didn't give me a chance to put in a name, and it just defaulted to that. Really was strange.
And who is asking about the X20?
Yeah, this is Cody. I'm with UTA AVD Lab. I remember me from an old contract a few years ago.
Awesome, welcome. I'll answer in the chat box there for you, okay? So we can move on with the rest of the program.
Appreciate it. Thank you.
Over.
Awesome. Great. Thanks. So our next presenter is Lois Ware. She's an aerospace engineer with over 40 years of experience in design, testing, and technology development of intake ducts for supersonic and hypersonic air breathing propulsion systems. She began her career at NASA Lewis, which is, of course, now Glenn Research Center, in the Propulsion Systems Directorate, where she tested many high-speed inlet models in the 1 foot by 1 foot and 10 foot by 10 foot supersonic wind tunnels. She later left NASA to become CEO and co-owner of Techland Research Inc., a small research and consulting business that provided air breathing technology development to NASA, the Department of Defense, and the aerospace industry. In July of this year, she returned to NASA Glenn as a senior technologist for hypersonic propulsion. Her duties include the support of hypersonic technology projects at the center, mentoring, outreach, and advising the center leadership on matters pertaining to hypersonic propulsion. So with that, Lois, I will turn it over to you.
Thanks, Mark. I appreciate it. Yeah, good morning, everybody. As Mark mentioned, I'm now Senior Technologist for Hypersonic Propulsion here in the Aeronautics Research Mission Directorate. But I feel for all of you out there, I've been where you are. Techland Research did many SBIRs over the years, both with AFRL and a couple of the NASA centers. We had several phase 1s, several phase 2s, and we even had one project go to phase 3 that resulted in a large-scale inlet test in the NASA Glenn 10x10 supersonic tunnel. So the program is great. It allowed me and my company to bring some technology ideas all the way to test in some cases. So it's a good program. And I'm glad to be talking to you folks this morning. My presentation is going to be a lot less technical than Jose's. I'm basically going to give you an overview of the NASA Hypersonic Technology Project, which I'll frequently refer to from here on in as HTP. A lot of acronyms on my slide, and I apologize for that. I'm going to try to explain all of them as I go. And before we leave this slide, I'd like to acknowledge my colleague, Francisco Sola Lopez, who's the Associate Project Manager for HTP. He assisted me in developing these slides. Next slide, please. This is just the outline of the discussion. It's going to be a really high-level presentation today, and along the way, I'll be highlighting some of the key Glenn Research Center contributions to the project. You'll hear me talk about RT1, RT2, etc. quite a bit as we go through. The acronym refers to research topics, and these are the major areas of research that are being conducted under the HTP umbrella. Next slide, please. This is a futuristic view illustrating a couple of general applications for air-breathing hypersonic vehicles where HTP technologies are going to contribute to the airspace. Commercial high-speed supersonic transportation is represented by the vehicle on the lower right there. Vehicles in this class could carry passengers across the ocean a lot faster than the current subsonic fleet can. With flight at Mach numbers between 2 and 5, we could reduce the time required for a transoceanic trip by several hours. So research being done under HTP is going to provide some of these technologies necessary to enable flight at the higher end of that Mach 2 to 5 speed range. There are other NASA projects that I'm not talking about today that are actually addressing the flight in the lower supersonic speed range. The other major hypersonic technology application of interest to NASA, of course, is air-breathing access to space by means of a two-stage to orbit vehicle, and that's shown on the left side of the figure here. The way we have achieved space access thus far is pretty much by using rockets, big rockets, and that's very effective and efficient rockets. But the problem with rockets is they have to carry both their fuel and their oxidizer that they need for combustion on the vehicle, and that makes them very heavy. So if we would go to a two-stage to orbit system like the one shown here, the hypersonic first stage vehicle would boost the rocket to the edge of the atmosphere using the air that it travels through as its oxidizer. Therefore, the takeoff weight is going to be a lot lighter than that of a conventional rocket. And then this fully reusable first stage would take off and land at a runway like a conventional airplane, which would allow for a lot more conventional basing. And because it doesn't launch from a rocket on the ground, it can potentially redeploy more quickly. However, the complexity of that hypersonic first stage is significantly greater than that of a conventional rocket. Otherwise, we'd already be routinely launching stuff to space this way. So the NASA Hypersonic Technology Project is addressing the technologies that we're going to need to make this two-stage to orbit space access vehicle a reality in the future. Next slide. The current project structure is given on this slide, and you don't need to look at all the details. The names are on here. The one thing I'd like to point out is you'll see that it's not just NASA Glenn performing this project. There are basically 3 NASA centers contributing primarily to this project, and they include Glenn Research Center, which is here in Cleveland, Langley Research Center in Hampton, Virginia, and Armstrong Flight Research Center, which is located on Edwards Air Force Base in California. In the green box, you'll see the technical challenges and research topics that NASA Glenn is actively working. And I've marked Glenn's primary contributions with the red asterisks here. I'm going to discuss each of these individually later, but I also want to point out that we do have significant collaborations with the Department of Defense. Obviously, the technologies that we're developing primarily for space access applications are many of the same technologies that the Air Force needs to develop their vehicles that they're interested in. And so by collaborating, we're working together and developing technology that the DoD and NASA can use. Next slide, please. This slide talks about our vision, our mission, and our approach. Yeah, you can just flip through all of those until the slide's full. There we go. Our vision here is to enable routine, reusable, air-breathing hypersonic flight. And the mission is to develop the core capabilities and critical technologies that are going to be required to master hypersonic flight in support of the U.S. enterprise. And then the approach that we're taking is to conduct not only fundamental research, but also to push our technologies more toward applied research to enable a broad spectrum of hypersonic systems and missions, including hypersonic, high supersonic transportation, and space access. The strategy is to develop our technologies to a technology readiness level of 6, meaning that we would develop fully functional prototypes or representational models that have been demonstrated in a relevant environment. And then the assumption is that industry would take it to the further level to actual full-size vehicle development. Our key partners, the key partners in this effort include NASA, other government agencies, including DoD, the U.S. aerospace industry, and of course, academia. Our long-term goals are to develop enabling technologies to TRL-6 for reusable hypersonic vehicles with speeds up to Mach 8 by 2035 and up to Mach 12 by 2040. And our primary enduring project priority is to support our NASA and our DoD partnerships and deliver on those commitments. Number 2 is to execute our technical challenges and deliver the critical technologies. 3 is to maintain ongoing NASA-directed research in order to sustain and grow our in-house competencies and capabilities. In other words, the NASA team will always be ready to address the newest technical challenge. And finally, NASA would like to lead the way toward the development of the next generation of U.S. hypersonic experts. Next slide, please. And you can flip through until that chart's full. Thank you. These are the basic HTP investment areas, the challenges, if you will, to reusable hypersonic flight. NASA Glenn is performing work in all of these areas except RT3. And we'll talk about all of them in the upcoming slides. I'm going to briefly discuss the contents of the 2 technical challenges related to RT2 in the blue box there first, and then I'm going to return to an overview of the 4 research topics before I conclude. So let's go to the next slide. Technical challenge 2, I think you're going to have to flip a couple more in this one also. There we go. Technical challenge 2 deals with turbine-based combined cycle, or TBCC propulsion technology. TBCC mode transition has been identified as a key enabling technology for TBCC hypersonic vehicles. A vehicle employing one of these propulsion systems uses a turbine engine to accelerate the vehicle from takeoff to some transition Mach number at which a high-speed engine, such as a dual-mode ramjet, would take over the propulsive responsibility and accelerate the vehicle on to higher hypersonic speeds. The blue blocks here describe the three major technology challenges of TBCC mode transition. Expanding the Mach range, both at the bottom end for the turbine engine and at the top end for the DMRJ. You can see in the charts at the bottom of the slide there. Currently, in the state of the art has a gap between those two, and what we need to do is extend the turbine engine up and the DMRJ down to the point where those two curves meet, and we can perform mode transition where those two curves meet in the middle there. So let's see. The figure on the left then shows one of these TBCC vehicles with the turbojet engine in the upper duct and the ramjet engine in the lower duct. There's a variable geometry surface that moves that initially directs the flow into the turbojet engine to take the vehicle up to the transition Mach number, and then that flap would close to redirect the flow into the DMRJ engine. The challenge is to safely perform that mode transition, and that's what NASA Glenn is focusing on in TC2, the actual process of mode transition itself. What we need to do is safely execute this process to keep both of the propulsion systems happy, and perform the mode transition such that we maintain thrust throughout the whole process, so that the vehicle can continue to accelerate to hypersonic conditions. So at NASA Glenn, we've done work on defining the mode transition process, making the inlet work. That's where I live. But we've also developed control algorithms that can control this combined system and that together operate as our TBCC. And the final task for this activity that we're actually involved in right now is demonstrating the mode transition process end-to-end with a live turbine engine in the low-speed duct and a simulated DMRJ in the high-speed duct. Next slide. TC3, I think there's a couple, yeah, there we go. TC3 is the newest technical challenge in the HTP portfolio, and this has to do with developing scaling laws for dual-mode ramjets. We can test DMRJ propulsion systems in ground test facilities and get really good information about how to design and operate them. However, future reusable hypersonic vehicles will be much larger, and combustion systems in particular don't just scale photographically. So TC3 is addressing how we're going to be scaling up our DMRJ engines from test size to demonstration vehicle size. The team is doing a combination of computational analysis to take a look at this problem, and then we'll also be doing ground testing to verify the computational predictions. And the ultimate goal is to develop a deeper understanding of the scaling process and to develop and define processes that will enable optimization of flame holding cavities in high-speed combustors, and thus enabling fully reusable larger hypersonic vehicles to work. Next slide. So going back to the research topics, research topic 1, its objective is to design and analyze hypersonic reference vehicles and use that mission analysis information or those designs to inform programmatic decisions and investments. This is done with a team of subject matter experts from all the disciplines that it takes to design a hypersonic vehicle. And because hypersonic systems are very multidisciplinary, we can't analyze just one part or one discipline or one set of flow physics that govern the operation of a single system while we're ignoring the others. So the goal of this research topic is to develop strength in all the areas of the aero sciences, from propulsion to vehicle structures and materials. And our goal is to build a strong design team that will be needed to design multiple systems and configurations for various missions. Next slide. RT2, this talks about the RT2 propulsion technologies topics that we currently have. Again, Glenn Research Center is performing work in the areas marked with the red dots on this slide here. One of the really important things we're working on right now is we're developing advanced pressure sensors for adaptive controls and health monitoring of hypersonic vehicles. As Jose made very clear, high-speed systems are inherently high-temperature systems, and therefore, we need instrumentation that works in these harsh environments. So we're developing high-temperature and pressure silicon carbide sensors that can tolerate those environments, and that's under RT 2.4. Under RT 2.8, we're doing high Mach turbine engine technology development. I think, as I mentioned earlier, TBC systems will require higher Mach turbine engines to accelerate from takeoff up to the mode transition Mach number, or the Mach number where the high-speed systems will take over. Also in RT 2.8, we're developing inlet bleed technology and nozzle technologies that are very important and relevant to that area. And then finally, in RT 2.9, we're doing ground testing of the Ether vehicle propulsion system, primarily to develop an experimental propulsion database that will be used in support of the RT1 mission analysis activities. These data will allow verification of the RT1 team's assumptions and provide them with realistic information about what the propulsion system can do. Next slide, please. Under RT3, the vehicle technologies are being developed, and this work is primarily being led and performed by NASA Langley Research Center. Next slide. RT4 is our high-temperature durable materials research topic, and Glenn Research Center is contributing to the 4 elements that are marked with red dots on this figure. The goal of this area is to demonstrate high-temperature material and component solutions and to provide experimental data and relevant lessons learned to contribute to the development of future reusable hypersonic vehicles. Glenn, in 4.1, Glenn is contributing to ceramic matrix composite joining technology development. This is a critical technology that's needed to join dissimilar materials, particularly for heat exchanger applications. RT 4.2 focuses on maturing high-temperature seal technologies. We've got a really strong seal group here at NASA Glenn, and seals are super critical for hypersonic vehicles. As an inlet technologist, seals are always one of my primary concerns in any inlet design, and it's particularly acute in hypersonic inlets because you don't want hot gases, being ingested in places where you don't want them, where stuff will melt. And so it's very important that seals, high temperature seals, work to prevent mission failures. And finally, 4.7 focuses on developing advanced alloys. And the Glenn team is working on start to finish alloy development and assessment, including powder processing, additive manufacturing, and tension creep and oxidation testing. Next slide, please. So in summary, HTP, the Hypersonic Technology Project, is working to enable routine, reusable, air-breathing hypersonic flight. And NASA Glenn, in particular, is contributing significantly in the areas of system-level design, analysis, and validation, propulsion technologies. Glenn is, after all, the NASA's main propulsion laboratory, air-breathing propulsion, and high temperature and durable materials. And of course, we do have existing collaborations with other government agencies, especially the Department of Defense. So thank you for your attention. Do you all have any questions for me?
Any questions? Let's see, again, you can come off of mute, you can raise your hand, or you can type something in the chat area if you would like, if you have a question. And Becky, you can help me out too if I miss somebody again here for that. Let's see. Well, maybe while people are typing or thinking, oh, do we have somebody?
Yeah, hey, Lois, I had a question. Jose Camaro's here, the one at Ampit.
Yeah.
A nice presentation. Of course, we're birds of a feather, as they say, and I definitely agree with the way NASA is approaching there, and very happy to collaborate and complement everything you guys are doing there as well. One of the things that I maybe I missed in the presentation. How are you approaching flight dynamics? As we know, when you go from subsonic to supersonic, the way that you model and characterize your vehicle from a stability and control perspective changes quite rapidly as you go hypersonic. No pun intended. Over.
Well, we're addressing at NASA Glenn, particularly in TC2, of course, the mode transition process, which is, happens at a high supersonic Mach number somewhere, between 2 and 5. And it's, the controls is a matter of maintaining control of the inlet itself, the preventing inlet unstart, and successfully, transitioning the flow to the high-speed duct. In terms of higher Mach number transitioning to higher Mach numbers and flight dynamics, I don't have a lot of experience in that area, and I know we're doing work there, but I can't speak to that. Probably shouldn't speak to that because I can't intelligently. So
that's great.
Thanks for the question.
If you can put us in touch with those folks, we are developing here at AMPIT a capability at the conceptual level to be able to understand the stability and control characteristics of hypersonic vehicles. And we've been partnering with some both a professor and students from Arizona State University, Professor Tim Takahashi, to help us map the sky, so to speak, given a vehicle. How can we understand essentially where its flight envelope needs to be, or where its flight envelope is, and then how we need to operate within that? Over.
I will look into that and I will get back to you, Jose. Thank you.
Excellent. Always great to see collaboration between our federal partners. We do have a question, Lois, from Ann Russell. It says that if we have technology to solve some of your launch problems, how do we share these, or should we go through the SBIR or challenge process?
NASA has a pretty robust SBIR program. I neglected to look up when the next call comes. That is the best way for small businesses to get in. I would say the other way is to reach out to the center's small business office, and I can look up that contact as well, to see, to get a contact made from within NASA.
Excellent, thank you. Any other questions from anybody? we'll wait here just a second to see if we have any other ones. I do have one question for you, maybe, and if maybe this can maybe be the last one before we go into our opportunity slides. But obviously, there's a tremendous amount of interest in hypersonics right now for that. Kind of curious, maybe, and this is obviously having to look in your crystal ball a little bit, but any thoughts on, what you think the future might hold? In other words, for those that have been living under a rock, we do have an election coming up here in a couple of months. Is there, and of course, every time there's changes in administration, sometimes priorities change and funding levels change. So I'm just curious for those listening, on any thoughts that you're willing to share, maybe in that area from a NASA perspective.
Well, one thing we know for sure is NASA's not going to pass its budget before the election, Congress is not going to pass our budget before the election. So we're for sure going to be working under a continuing resolution again until probably well into the next calendar year. So there's that. But no, seriously, I think, I've been in this for 40 years. I worked the NASA program. I've seen hypersonic technology peak and wane at least twice now. And, it's hard to tell when those things are going to happen. When that happens, it's a bad thing. I've seen a lot of really smart people with a lot of expertise just leave the field, especially in industry, because when the big contracts, are canceled and, the funding dries up, those people have to go somewhere, and some of them just leave the field. So, our challenge in government for sure is to maintain some level of expertise, because industry won't do it. Will hypersonics continue to be important? I think it will, probably for a good while now, mainly because we know that our foreign competitors and or enemies for sure are working the area pretty hard too. And I think our government, regardless of the outcome of the election, I think the government recognizes that if we're going to stay in the lead in this game, we've got to stay in this game. So I feel pretty confident that I'm going to get to the end of my career on this wave at least. And I hope that this wave lasts a little longer than maybe some of the previous ones did. Thanks.
Excellent. Great. Yeah, I agree with that. Jose?
Definitely agree. And one other thing I wanted to add to that to Lois, workforce development is a significant portion of where DoD is supporting hypersonics, as you know, Mark, through OFRN. And we have a great resource here near Wright Pat in Ohio with Cincinnati, University of Cincinnati, Wright State, Ohio State, University of Dayton, even Purdue. We let them come over state sometimes as well. We provide, we can deliver workshops, short courses, and even lunch and learn type of activities for anyone that's interested through the network to support and encourage understanding hypersonic systems technology. Over.
Awesome. Yep. Thank you so much. Appreciate that. Anne did have one follow-up, so we'll go ahead and maybe answer that. She just asked, where's the primary test and evaluation being done for materials for NASA or AFRL?
NASA or AFRL?
I was at you for NASA, and Jose can answer for AFRL.
Yeah, it's primarily happening at NASA Glenn. We've got certainly the SEALs work is happening at NASA Glenn, and a lot of the materials work is happening at NASA Glenn also. Yes.
Awesome. Jose, how about AFRL?
I was typing in the chat too, but right here, right past an Air Force Base in the Materials and Manufacturing Directorate. afresearchlab.com. Check out the Materials and Manufacturing Directorate link from there.
Awesome.
Over.
Thank you so much. Awesome. Fabulous. Thank you so much. Thank you so much to both of our presenters today. This has been outstanding. So I have thoroughly enjoyed it. Even though, although Jose's presentation sort of had flashbacks for me 40 years ago when I was sitting in my aero engineering classes at Ohio State. So, but I appreciate that. That was excellent. Good reminders for me for some things that I had probably had forgotten a long time ago. Just as a quick reminder too for everybody, yes, the briefing will be posted. There'll be a link to the presentation as well as the briefing on the OFRN website once Becky gets all that taken care of. So in the next couple of days, you can check the OFRN website for that. You can, Becky, if you can go ahead to the next slide, and I will turn it over to Morgan and let her talk about the opportunities that she was able to find for everybody.
Thank you, Mark. First, I just wanted to thank Dr. Cambrousse and Lois for the wonderful presentation. I hope that everyone was able to get some valuable information from that. But my name is Morgan. I am an OFRN intern, and today I want to share with you some funding opportunities that pertain to the material and hypersonic system research. So let's jump right in. The first opportunity that we have was posted by the Naval Air Warfare Center. They are interested in receiving white papers for advancement and improvement of naval air warfare operations, with priorities given to hypersonic system research. It is open to all, and there is no restrictions. It was recently posted this past June and won't be due until the following June of next year. They are looking at around $160,000 to $200,000 for multiple awards. Specifically, they're looking for research in hyperspeed aerodynamics, multi-physics modeling, hypersonic systems, high temperature and specific strength materials, structures and coatings, guidance, navigation and control, and advanced air breathing propulsion. But they are not limited to these specific areas. Next slide. So the next opportunity we have has been posted by the Naval Sea Systems Command, but more specifically, the Naval Surface Warfare Center Crane Division. Crane specializes in support in three broad focus areas: expeditionary warfare, strategic missions, and electronic warfare. They are looking for white papers for hypersonic weapon systems, research to include aerodynamics, aerothermal prediction and analysis, navigation and control, high temperature materials, thermal management, sensors, and sporting algorithms. So the funding does depend on the technology area and the technical approach. It is also a broad agency announcement. It was released in February and will be due this upcoming February of 2025. Next slide. The next opportunity we have has been posted by the Air Force Academy. USFA High Performance Computing Modernization Program is looking for white papers and proposals to improve computational simulations of hypersonic vehicles in support of the DoD. Their goal is to improve computational simulations approaches, including numerical methods, modeling approaches, and simulation of a variety of aerothermal dynamic and propulsion aspects of hypersonic flight. Their specific areas of interest are not limited to turbulence, boundary layer transition, fluid structure, thermal interactions, non-equilibrium chemistry, ablation, and combustion. There has not been a specific award amount, but the ceiling is set at $99 million. It is also a BAA, and there is not a due date for this, so they are accepting on a rolling basis. Again, there is no eligibility. Next slide. So next we have another BAA that's been put out by the Department of Defense, U.S. Army Space and Missile Defense Command. The areas of interest include, but are not limited to, tactical response space and defeat. Tactical response space and high altitude technologies, test and evaluation, strategic weapon technologies, and hypersonic defeat. Please note, under the where section, that only the revisions made to the BAA will be posted on grants.gov or the sam.gov website. This was recently posted in August and will be due August 26th, 2029. Next slide. So this has been posted by the Air Force Defense Research Science Program. The eligibility is a little more stricter than the other opportunities. It is open to nonprofits, public and private institutes of higher education, and small businesses as well. This is a BAA and a contract. They are looking to fund up to $750 million awards. Their goal is to perform research and development on agile weapons, airframes deployed and dispensed from unmanned or manned platforms. The areas of interest are agile weapon airframes for high-speed flight, high agility airframes capable of aggressive flight maneuvers, networked collaborations, compressed carriage munitions and release mechanisms for small weapons, and small weapon design, carriage, and dispensing technology. This was released in March of 2022, however, it was updated this previous July, and it's not looking to be due until March of 2027. Next slide. This opportunity has been posted by the Office of Undersecretary of Defense Research and Engineering Joint Hypersonic Transition Office. They are partnered with Texas A&M Engineering Experiment System and University Consortium for Applied Hypersonics. They're accepting white papers for acceleration of hypersonic technology research, the development of a national hypersonic workforce, and the transition of ready technologies into operational capabilities. Areas of interest are rotating detonation engine advancement, duration seals for extreme environments, seeing through high-speed turbulence for EO seekers, non-kinetic methods for integration, air and missile defense, and jet interactions in hypersonic flight. So this was previously posted as well. The notice of intent is coming up on October 11th. However, the prototype proposal submission deadline is about a month after, on November 15th of this year. They are giving about $9 million, but it does depend on the topic. This is a contract. Next slide. So this is a little bit different than the rest of the slides. This is a new announcement called the Multiple Authority Announcement. So it is pretty much a combination of BAAs, CSOs, FOAs, and these US codes. There are 3 different programs that they have, 2 of which do apply to hypersonic systems. The first one is Photonic Electronic and Soft Materials Division. They lead research and development activities of materials for the advancement of battle space awareness and sensing, materials for enhanced electromagnetic spectral dominance, and advanced materials and processes to support contested logistics. And then their other program is the Manufacturing and Industrial Technologies Division. Their goal is to identify, prioritize, and integrate DAF industrial-based requirements to provide the manufacturing processes, techniques, systems, energy, and equipment needed for acquisition, production, operation, and repair of the DAF. For more information, there is a link here. Once these slides do get posted, feel free to look at these if you are interested. Next slide. And then lastly, I just wanted to touch on this. This is the new 2025 Department of Defense SBIR STTR BAA release schedule. So this October, there will be a new schedule change. There will be 12 releases over the span of a year. They will be posted the first Wednesday of every month. So please note that some of the dates have changed from previous notifications. The schedule is posted here, so feel free to take a look at that. And for more information, there is a link below to read up on it. Do I have any questions?
Awesome job, Morgan. I don't see any questions. Oh, wait a minute. Jose?
Yeah, it's Morgan, on the due dates on some of these, they seem kind of far off in the future. Is the due date more like when the opportunity closes and one can submit proposals kind of like on a rolling basis? Do you know what, can you clarify on that? Over.
Yeah, so the dates that you're talking about have been posted on their websites. If you do have any more questions about whether they're still accepting them, I would definitely reach out to the contact information listed on each slide. If they do have a date, that is what they have put out. But for more specific information, I would definitely reach out.
Yeah, in general, Jose, just from my experience, is that that it's probably a more of an open rolling type of an application when they have like 4 or 5 years for between an open date and a due date. All of the federal agencies do those kinds of things for it. So, as opposed to what you're looking at, on this slide here for the Cyber Sitter type stuff, where you can see between open and close. Typically is a month, or sometimes it might be a little bit more than that, but a lot of times for the Small Business Administration, their dates are very tight compared to federal agencies, whether it's DoD or DOE or NASA or any of the other federal agencies that participate in the Small Business Administration. Sometimes they have large windows. All right, excellent. I think that is it then. Next slide. Just some helpful links that we always include on the last slide here for your use. Again, the slides will be posted on the OFRN's website. Next slide. And upcoming events, these are just some things that are going on. It's not all inclusive. It's just events that either that Parallax individuals like myself, I'll be at the AFA's National Convention next week in DC. But there are a lot of other, the AFA Aerospace and Cyber Conference is the one I'll be at, not the National Convention. But there's a lot of other things, of course, going on. Some of them deal with hypersonics. Others deal with things that are here in the state of Ohio that you may be interested in. So if you haven't seen some of these before, I would highly encourage you to Google the name of the conference, and you can check it out on their website. And next slide.
The other thing, Mark, if I can, is the Air Force is celebrating its 77th anniversary next Wednesday, and the Air Force Museum is having some special things going on in there for anyone that's interested. Over.
Excellent. Yes. Air Force Museum is always an awesome place to go to. So, but you need about 3 days if you really truly want to see the whole thing and read everything. Okay. Well, thanks so much to everybody. Thanks so much, of course, to our presenters, Dr. Camberos and Lois Weir. So we truly appreciate the time that you took out to spend with us today and all of our attendees. I hope everybody has a great rest of your Thursday and weekend, and we'll look forward to hearing and interacting with you in the future. So thank you so much.
Thank you.
Thanks for hosting, Margaret. Thanks, Becky. Over.